chapter, we're going to look at logs and exponents. And this section will look at the secret to logs, and we'll look at the graphs of those. So the secret to logs is people have a love-hate relationship with logs. They either love it or they hate it. And most of the people that hate it are missing just this basic point, is that whenever you are looking at logs, if you can go from exponent form to log form, you're going to be able to understand logs. So exponent form would be something like 2 to the x is equal to 8. All right? Now, if we want to turn that into log form, what you do is 2 is my base. X is my exponent. And 8 is my number. Sometimes they call it the argument. So what we're going to do is we're going to change this into log form. So what you do is you say it's log base 2 of the number 8 equal to the exponent, because logs are exponents. So notice we still have the base down here, as we have the base in the exponent form. Logs are exponents. So when we look at the exponent, what we're talking about is x is the exponent. That's the answer, because logs are exponents. And then our number is just the number 8. Okay? So if you can go from exponent form to log form, or log form to exponent form, you can get yourself out of little jams that can help you solve and do all kinds of different things. So let's do a couple. I'm going to do these practice ones. This is in exponent form. Log base, here's the base, 4 of the number 32 should be equal to 5/2. So 4 is the base, 32 is the number, 5/2 is the exponent. Logs are exponents. Same thing with this one. Log base 10 of 0.001 will be equal to the exponent -3. Now we can do the log form to exponent form. Base 25, logs are exponents, so this is the exponent, 1/2, should be equal to the number 5. And it sure is, isn't it? Now, if you don't see a base, calculators and problems will assume it's base 10. So base 10, logs are exponents, to the second will be equal to 100. And we know that's true as well. So you should be able to do those. And then on the next page, all of these, what you're doing is you're trying to set these equal to x, and then I would rewrite them as exponents or as logs, and then see if you can solve. For example, base 3 to the x is equal to the number 27. 3 to the x equals 27. So we can see that x is going to be 3. Again, if you don't see a log, it's base 10, but if you see ln, it's base e. If you set this one equal to x, you get x equal to 36 to the log base 36 to 216. Looks really hard, but if you write it in log form, log base 36 of x will be equal to log base 36 of 216. And so x has to be 216, because log base 36 equals log base 36. Those numbers have to be equal. So that'll help you with some of those more difficult ones. Then, once you finish those, there's a domain here, and just a quick little reminder that for a log graph, log graphs look like this. go through the point 1, 0, and never makes it past here, never makes it negative, never gets there. We can see this because if you went log base 10 of 10, you get 1. Log base 10 of 1, you get 0. 1, you get 0. Log base 10 of 0, put it in your calculator, it'll say no answer. Likewise with log base 10 of negative 1 or negative 10. Okay, so what do we do? Well, we know that the domain has to be greater than 0. So 4x plus 8 has to be greater than 0. So if it's greater than 0, 4x is greater than negative 8, x is greater than negative 2. And you would do that with all of these. These have to be greater than 0. So how are you going to do this one? X plus 2 over x squared minus 1 greater than 0. Well, you're going to do exactly what we did last chapter. You're going to draw that number line. The 0 is at negative 2. The vertical asymptotes will be at negative 1 and 1. So you're going to test these areas. And see if it's plus or minus. If it's plus, it'll be true because it'll be greater than 0. If it's minus, it'll be not true, and so you wouldn't include it. You'll probably have an interval with a union. That's what you'll have. So that's it for that assignment. We're going to keep going. We're going to give you a little puzzle here to start with. Let's say I had 1 microbe I set in a jar, and after 1 minute, it doubles to 2. And after another minute, it doubles again, and doubles again, doubles again, and keeps every minute doubling and doubling. Well, at 5 o'clock, it's completely jam full of microbes. Totally jam full at 5 o'clock. What time was it half full? Well, this is 9 hours from 8 till 5. See if you can figure out what time it was half full. For graphs, exponential graphs, I want you to be able to find domain and range. So for this one, 2 to the x looks like this. It goes through 2 to the 0. 2 to the 0 is 1. So you have 0, 1 as a point. And if you go 2 to the negative 100, it's going to get really close to 0, but it'll never get there. So as we went to negative infinity, the y value is 0. But when we go to positive infinity, that's going to go up to infinity. So my domain is going to be all real numbers, no exceptions, but my range is going to go from 0 to infinity. That's 2 to the x. Well, we can do 2 to the negative x, or when this base is between 0 and 1, the fractional, let's look at 2 1/2 to the x, or 2 to the negative x. Well, 2 to the negative x is still going to go through 0, 1. It still does that. But this, as x goes to negative infinity, it's going to go up to infinity, and as it goes to positive infinity, it's going to go to 0. So my domain is still all reals, but my range is 0 to infinity. So we have the same range and domain, it's just flipped over that y-axis. Okay, talk a little bit about a special base. The special base is base E, and we want to see what that graph looks like. If you put in your calculator 1 plus 1 over 1 to the 1, you're going to get 2. 1 plus 1 over 10 to the 10, or 100 to the 100, or 1,000 to the 1,000, you'd think it'd just keep getting bigger, bigger, bigger. But what it does is it levels out to a number called 2.71828. Goes on and on forever like E. It's the second most popular, most used constant in mathematics. So if you wanted to see a graph of y equal to e to the x, seems like it should be hard, doesn't it? But look at this. Here's 2 to the x. Goes through 0, 1. I want you to remember that. Here's 2 to the x. Here's 3 to the x. Okay? So where do you think e to the x is? Well, remember this is 2.71828 to the x. Well, that's really close to 3. So it's going to be between 2 to the x and 3 of x, but it's going to be closer to 3 to the x, which is e to the x. So if someone asks you to draw e to the x, just draw 2 to the x. It'll be the same. Domain, all reals, range, 0 to infinity again. Okay, there's e to the x. And you could go e to the negative x, and so on. Well, here's sketching graphs. Here's 2 to the x goes through 0.01. And then if it's plus 1, just moves this whole thing up 1, which turns this into 0.2. Has an asymptote. Instead of y equals 0, it'll be y equal to 1. E to the x, remember e to the x goes through 0.01. If it's minus 1, just goes down here. And the asymptote is going to be, oh, that's weird. Asymptote, I better draw. Asymptote is going to be at y equal to negative 1 instead of y equals 0. And this goes through 0, 0, doesn't it? All right. And you can manipulate those. I do want to do one more, and this is log base a of x equal y. Now, just looking at that, it looks pretty scary. But take a look at this. Log base a of x, if we write this as a to the y equal to x, and we switched x and y, doesn't this look very much like 2 to the x or 3 to the x or e to the x? But if you switch the variables, what you're doing is switching the points. So this is going to be 1, 0 instead of 0, 1. This is y equals 0. Switch x and y, you get x equals 0. And now when you draw that curve, you'll see a nice symmetry between those two graphs. And this is going to be y equal to log base a of x. It's the inverse of y equal to a to the x, just switching those variables around. Because they switch the variables around, the new domain is only going to be 0 to infinity, and the range is going to be all reals. Does that look familiar? Yeah, that's the switch, the flip over switch of a to the y. And by the way, if you have natural log, that's log base e, 2.7. It's just going to be, well, let's look at that real quick. So here's log base 2 of x going through 0.10. Here's log base 3 of x. That goes through 1, 0. So if you're trying to draw log base e of x, that's going to be close to the log base 3 of x and kind of similar to what we saw with e to the x. And you can shift graphs left and right if you want, or up and down. Let's do this one real quick. Log base 4 of x goes through 0.10. Has an asymptote here of x equal to 0, vertical asymptote. Now, if we shift everything to the left 3, 1, 2, 3, Now we're going to be sitting at -2, 0. Have an asymptote here at x equal to -3. And there it is. There's your graph. All right, we'll get to those properties for a little bit. So you're going to get a chance to graph these side by side, do their shifts, maybe some flip overs, good stuff. Finding inverses, remember y equals 3 to the x plus 2. You just switch those, x equals 3 to the y plus 2 minus 4, and then you figure out how algebraically you can solve for y. Changing from exponent to log form might happen at one point. Just want to talk about applied problems. This is where it gets good. You have a Richter scale. Numbers are very spread out for a lot of things. Like let's say you have some measurements that are 10 marks to, a billion marks. Okay, that's quite the range. But if you go 1 times 10 to the first compared to 1 times 10 to the ninth, and you scale these with the exponents, now you can compare these really huge things to each other, and that's where the log comes in. And don't forget, if you see log, no base, it's base 10. Natural log is log base e. It says show that m of 0.001 equals 0. So log base 10 of 0.001 over 0.001 should be equal to log base 10 of 1, which is 0. Good. You can put 80,000 in your calculator and see what that comes out to be. It says show that an earthquake registering 6.7 equals log base 10 x over 0.001 is 10 times greater than the measurement of 5.7. So here's 5.7 equal log base 10 x over 0.001. Okay, so again, whenever you're stuck, change it to form. This is log form, change it to exponent. 10 to the 6.7 equals x over 0.001. This is 10 to the 5.7 equals x over 0.001. So how do these differ from each other? All that you have to do is say 6.7 is 5.7 plus 1, right? And 5.7 is 10 to the 5.7 times 10 to the first, x over 0.001. So can you see why this is 10 times bigger than this one? Find 2 news stories, recent earthquakes which give magnitudes. How many times larger is it? So give this a try. Go online and see what you can come up with. Here's a problem you can do with decibels. Remember, log base 10 when you don't see a base. And then this one, it's a little hard to see, but this is your formula. pH equals negative log base 10 of the concentration of hydrogen ions. So if you know the number goes in here, take the log of that, take the opposite, you get the pH. And you can answer those questions. So much for the first unit on logs. Good luck with those problems.